Hey everyone, and welcome. Today we're diving into a really wild concept, something that tries to link physics, mathematics, and even information itself into one unified system. It's called the multicode. So let's explore what happens when you treat the universe like a piece of code. So let's just start with a huge question right off the bat. What if code isn't just for our computers? What if it's the hidden language of everything? Physics, math, matter itself. That's the idea we're going to unpack today. A code that's not written in ones and zeros, but built from the actual building blocks of the cosmos. Okay, to get this, we have to start with a really simple but powerful idea: resonance. And you already know what this is. Think about pushing a kid on a swing. You can't just shove it whenever you want. You have to push at that perfect moment, right? When you do, the swing goes higher and higher with barely any effort. That perfect timing, that incredible amplification, that's resonance. And it turns out it's the universe's absolute favorite way to move energy and information around efficiently. So if resonance is the key to the whole thing, then what's actually vibrating? This first part is all about tracking down the universe's most fundamental note. In physics, that basic note, that fundamental vibration, is modeled by something called the harmonic oscillator. It sounds fancy, but really it's just a model for anything that wiggles back and forth around a stable point. Like a guitar string, a pendulum, or even the bonds holding atoms together. It's the simplest, most universal model for vibration that we have. But this is where things start to get really, really weird. See, to build something like the multicode, we can't use a regular old guitar string. We have to shrink down, way down, to the bizarre world of quantum physics and right into the core of the atom. So let's take a look at the ingredients we're going to need. And check this out. This slide really shows how different a vibrating atom is from anything we're used to. In our world, energy is smooth, like a ramp. But in the quantum world, it's a ladder. It can only exist on specific rungs, in discrete steps. A quantum oscillator is never, ever perfectly still. It always has this little hum of zero-point energy. And, get this, it can literally tunnel through barriers it shouldn't have enough energy to cross. It's those discrete energy steps, those rungs on the ladder, that are absolutely perfect for storing information in nice, clean, countable packets. Okay, so the theory is cool, but you can't build a code out of just ideas. You need actual hardware. You need a physical material that has all these bizarre quantum properties baked right into it. And the search for that perfect material takes us deep inside the atom, right into the nucleus. And the element we're looking for is samarium, specifically these three different versions, or isotopes. Think of them as a team. Samarium 150 and 152, they're the stable, reliable support crew. But the real star of the show is samarium 151. It's radioactive, and its nucleus has this incredibly unique set of energy levels that are super sensitive to neutrons. If you hit it with a neutron, its state changes in a really precise, measurable way. That makes it the perfect active ingredient for encoding information at the nuclear level. And just when you think it can't get any stranger, it does. Inside a nucleus like samarium, you can trigger this collective vibration called the scissors mode. The protons and neutrons literally start oscillating against each other, kind of like the blades of a pair of scissors. This isn't just one little particle vibrating, it's the entire nucleus acting together as a single unit. This gives us yet another layer for storing information, not just in one particle, but in the collective behavior of the whole system. It's wild. All right, so we've got our quantum hardware. Now we need the software. We need a mathematical language that can orchestrate all these physical vibrations and give them a precise, predictable rhythm. And that language comes from a corner of math called number theory. The tool is something called the Carmichael function. The best way to think about it is like a master clock for the whole system. Or maybe it's sheet music. It's a way to calculate the precise cycle time for any given system, the exact moment when everything repeats. For the multicode, this function makes sure that the mathematical timing of the code lines up perfectly with the physical resonance of the atoms. It's the harmony between the math and the physics. Now, to make the whole system more efficient and a lot tougher, it borrows a pattern that you see everywhere in nature: the Fibonacci sequence. I mean, we see this in seashells, in the petals of a flower, in spiral galaxies. It's everywhere. And in the multicode, this sequence is used to cut down on noise and interference. And amazingly, it even allows for self-repairing data. If a little piece of information gets corrupted, the underlying Fibonacci structure actually lets the system figure out what's missing and reconstruct it. Okay, we have the physics, we have the math. Now it's time to put it all together. This section is all about forging the final architecture of the multicode. So where on earth do you store information that's this complex and this delicate? Well, you need a place that's about as clean and quiet as you can possibly get. And the answer is one of the weirdest states of matter in the universe, a Bose-Einstein condensate. This is what you get when you cool a cloud of atoms down to just a tiny fraction of a degree above absolute zero. They literally stop acting like individual atoms and start acting as one giant, coherent quantum entity, a superatom. And the level of precision you can get is just unbelievable. Experiments have actually shown you can take quantum information, say, from a single particle of light, and transfer it into one of these condensates with 95% fidelity. That's a near-perfect translation from light to matter. It's incredible. So here it is. This is how it all stacks up in the final 5-layer architecture. At the bottom, you've got the physical layer. That's our Bose-Einstein condensate, the actual hardware. On top of that is the energetic layer, where we're actually encoding data onto those discrete quantum energy steps. Then the statistical layer uses that unique samarium nucleus to generate super random cryptographic keys. The mathematical layer is our master clock, the Carmichael function, keeping everything in perfect time. And finally, the cryptographic layer on top uses quantum entanglement to create security that is, quite literally, unbreakable by the laws of physics. Each layer builds perfectly on the one below it. Now, a system this powerful, well, it obviously comes with some mind-blowing potential, but it also has some equally enormous challenges. So let's take a clear-eyed look at both sides of the coin. On the one hand, the promise here is, frankly, revolutionary. We are talking about storing information at a density that makes today's tech look ancient. Because it runs on resonance, it's unbelievably energy efficient, it's naturally secure thanks to quantum mechanics, and because that whole condensate acts as one thing, you get massively parallel processing for free. It's a huge leap forward. But here's the reality check. This system is incredibly fragile. You have to keep it colder than deep space, near absolute zero. The math behind it is just staggeringly complex. Building the hardware is a huge technological and financial challenge. And oh yeah, our star player, Samarium-151, it's radioactive. It slowly decays, which means your storage medium literally has an expiration date. And that brings us to our final and maybe most important section. What happens if we actually pull this off? What are the ultimate consequences of creating a code this powerful? Are we crossing some kind of line? One of the source documents puts it in this really haunting way. It says, the research hints at structures where the boundaries between subject and object, between stored information and the storing medium, begin to blur. Think about that for a second. At that level, is the code just data sitting on the matter? Or is the code becoming part of the matter itself? I mean, if you follow this to its logical conclusion, you end up in some serious science fiction territory. We're talking about matter programming, the ability to literally change the properties of a material in real time. Or biophysical resonance. Could this code talk directly to the molecules in our own bodies? And the final step, a potential language that could create a direct interface between a human brain and a machine. And so that leaves us with this final, really critical question. In trying to build the multicode, are we just learning to speak the native language of the universe? Or, by blurring that line between information and reality, are we accidentally building a monster that we have no way of controlling? That is something to think about.